video so that you can see this. All right, so I erased a lot of the work, but I left some stuff up here so that we could continue. I'm still using this example to demonstrate. So I have, these were the 5 data values we had, and we added them. Then we used that to get the sample mean. And so we did mean, median, and mode. And then we did the range on this. I guess I should put range up here also. We did the range, which was 90 minus 60, so the range was 30. That's the high value minus the low value. Then I did the work for the variance, but I've erased it because it takes up the whole board. But this was the answer we got for the variance, and that's unrounded. I didn't have to round it because it was already to the 10th place, which is what I wanted, but I didn't round anything as I was doing that one. And that brings us to the third measure of variation, which is standard deviation. Now, standard deviation is really just a form of the variance. In fact, you have to have the variance to find the standard deviation. If you look at your formula sheet, so I'm going to share that again. And I want you to look at standard deviation. There's 2 different ones. So we have number 2 is the population standard deviation. And notice it's called sigma, and it's just the square root of sigma squared. And then the sample variance is called S, and it's the square root of S squared. So we're now going to look at this. Sorry about the squiggles. And this. All right, now, so you see the formula for standard deviation is just to take the square root of the variance. So let's write that down. So for variance, remember I told you that it's sort of like averaging the squares of the distances from the mean. Okay, so standard deviation is, and we can actually write a definition for this in words, is the square root of the unrounded variance. Now this is actually true whether it's population or sample. And at this point, you don't have to worry about which one it is. When you're doing variance, it matters whether it's a population or a sample, because for sigma squared, for the population variance, you divide by n, but on the sample variance, you divide by n minus 1. So you have to be careful with that. But once you have the variance for the population or the sample, at that point, you find the standard deviation the same way, by taking the square root. So, for example, for population, the population standard deviation is lowercase sigma, which is just the square root of sigma squared. You'll see a lot of other stuff on the formula sheet, but that's because it's just a repeat of the formula for sigma squared. And then for the sample variance, sample standard deviation, sorry. Sample standard deviation, that's just a little s, and it's the square root of s squared. In both cases, we want to make sure that that number that we're taking the square root of is not rounded. So we may round it when my stat lab, or when I ask you for variance on a test, or if it's in a homework assignment, they may tell you to round that variance. But when you find the standard deviation, you should not use the rounded answer. You should use the unrounded variance. So let's find the standard deviation for our example. The standard deviation for our example, since it's a sample, so we're going to use this here. Since our example is a sample, we're going to use this formula. And for our example, the standard deviation, which will be little s because it's a sample, is going to be the square root of the unrounded variance that we got. So from that example, that's the one I did right before the break, the unrounded variance was 156.8. Then, so this is easy, okay, because this we're just going to punch in the calculator. The only thing that's complicated, or it's not really complicated, but it's kind of, it takes time, okay, and there's a lot of room for mistakes. You have to punch in a lot of numbers. The only thing that's a little bit hard is that variance, but like I said, it's one of the only complicated formulas we have. I should say maybe it's probably the most complicated formula that we're going to work with in this course. So I'm going to take the square root of 156.8, and that gives me a big old long decimal number. I'm going to write down several places that it goes on. So obviously I need to round this. Well, good for us, the default rounding rule. In other words, this is what we're going to do if nobody tells us what to round to. Now, my stat lab will often tell you what to round to. So if it always round to the place that my stat lab says to round to. But if no one's telling you what to round to, we're going to go with the same default rule that we did for mean and variance, which is one place past the data. Remember, here's our data right here. This is our original data. Since they're whole numbers, one place past, so that's the number that's in the whole number place. We're going to go one place past that, so we're going to round that. And to round that, we only look at the very next number. The other numbers are irrelevant when rounding this. So when you're rounding a number, you only look at one number after it. And so what I'm going to give for my final answer for the standard deviation is 12.5. And the next thing we're going to do is talk about what that means. Okay? So if you have a question about how I got the variance, be sure and rewatch the video once I get it posted. And by the way, you can watch the videos even before I post them in my math lab by going to online class meetings, and you click on the 3 bars and click on recordings, and then all the things I've recorded will be right there for you. You just choose the one you want to watch, and you can watch it from there. It doesn't have to be in my stat lab. And when I say my math lab, my stat lab, it's the same thing, guys. So hopefully that doesn't confuse you. So this is our standard deviation. But what does that mean? Okay. So this is an important thing, and this is what leads us to the other 2 theorems that are in this section. And as it turns out, in all data sets, almost all of the data values will be within 3 standard deviations of the mean. Now, the reason why I'm saying this is because, and I'm leaving up the mean that we found here. Remember, the mean was 79.4. One standard deviation is 12.5. So I'm going to call that's one standard deviation. Now, if we know stuff about the data set, for example, if we know the data set is like, if you made a histogram, if that histogram was bell-shaped, then that tells us something about how spread out the numbers will be. If it's not bell-shaped or we don't know what the shape of it is, then we could still say some things about it, we just can't be as exact. Okay, so if you know that a data distribution is bell-shaped, in other words, the histogram or the frequency polygon is bell-shaped. Bell-shaped means it looks kind of like this. Upside down bell. If it's bell-shaped, then we can use something called the empirical rule. If it's not bell-shaped, or if we just don't know what shape it is, then we can use something called Chebyshev's theorems. Those are the last 2 things we're going to talk about today. So we're going to talk about and what the meaning of this standard deviation is. So I think what we'll do is we'll pretend first that it's bell-shaped. So we're going to pretend this data set is kind of bell-shaped. And it might be somewhat bell-shaped, so that may not be. So notice the frequency. If you looked at these individual things, there's one of these, one of these, one of these, and two of these. And it kind of goes up and down. So it might be, actually, it's going to be, the frequency is 1, 1, 1, 2. So that's not actually an interesting shape. But we're going to assume, so let's assume we don't really know the data values. And I'm going to use this and the mean. And I'll use that as an example as we discuss the empirical rule and Chebyshev's theorem. And by the way, I've already made videos about both of those things. So if you don't totally understand today what I'm talking about, then be sure and watch those videos. And they're posted in Blackboard, but I am going to have those fixed, and I'm going to put all the videos I have made, including the recorded videos from today. I'm going to put them all in a recording assignment for 2.4. And I also had previously, before school started, I had made a video about 2.3, mean, median, and mode. And so I will include that as well. I'm just going to put everything in a recording assignment for you. But there are videos already in Blackboard in the Unit 1 folder. So you can look at those, or you can wait until I get them posted in my stat lab. So the first thing we're going to look at is the empirical rule. And sometimes it is called, if you may have seen on your checklist planner, I don't know if I put it on there or not. The empirical rule is the 60, 68, 95, 99.7 rule. And if you look in Blackboard, guys, you will see this. I never can remember if I got that first number, if it's 68 or 65. But I do have an empirical rule image I'm going to share with you. And I'm going to share this again. Yeah, 68, 95, 99.7 rule. This is actually a page out of your book. It's page 33. I think it's either page 33 or it's slide 33. I'm not sure which. And what this is demonstrating to us is that if you have the mean in the middle, hopefully you see that X bar there. In the middle, notice this is for a bell-shaped distribution. So the empirical rule applies only to bell-shaped distributions. And I'm going to choose a different color. And notice that X bar is in the middle. And notice it is the highest frequency. Do you see the height of this, the frequency of the mean is the tallest. It's the highest thing on here. And then as you move away from the mean, you see that the data values are less and less likely. So the S, remember, is a standard deviation. So you'll notice they went X bar plus 1S, X bar plus 2S, and X bar plus 3S to the right. And then going to the left, they went X bar minus 1S, X bar minus 2S, and X bar minus 3S. And we're going to do that on our example in just a minute. And what this empirical rule says is that if your data distribution is bell-shaped, that 68% of the data values will lie within one standard deviation, meaning one to the left or one to the right. So you see that between here, that blue section in the middle is 68% of the data values will be there. Now remember, this is only if the distribution is bell-shaped. And then let's do a different color here. Let's do purple. 95, whoops, it didn't change to purple. Let me change to purple. 95% will lie within two standard deviations. Notice that's almost everything. So here's x bar minus 2s and x bar plus 2s. So across there, 95% of the data will lie between those two numbers. And then the last one, and notice that means only 5% of the data values will be more than two standard deviations from the mean. This is the value of a standard deviation, because this is what we use to determine if something is unlikely. Is it unlikely for someone to, say, test positive for a particular condition? Is it unlikely? Then what you would need to know, it's going to be unlikely basically if less than 5% of the population would test positive, then it's unlikely. So then the last one, when you have a bell-shaped distribution, 99.7%, so almost 100%, will be within 3 standard deviations of the mean. So that's going all the way across, all the way from here to here, okay? Within that, and I'm going to show you what that means on our example. I've just made a big old mess out of this, but I can erase it. So this is I think this is probably a slide in the PowerPoint, but if you want to print this off, it's pretty helpful, and it shows you how the 68% is divided in half and so forth. So I'm going to unshare this and reshare the video so we can look at what that would mean on this one. So the empirical rule applies only to bell-shaped distributions. And so we're going to just assume this was bell-shaped. And so if it's bell-shaped, so I'm going to draw a bell-shaped distribution. These are my x's, and the mean should be the value with the highest frequency. Our mean was 79.4. I'm going to put that right here in the middle. That's x bar. And then I'm going to take this standard deviation of 12.5 and I'm going to add it to the mean 3 times to get the number that's 1 standard deviation to the right. So I'm going to do 79.4 plus 12.5. So that would be 91.9. That would be 1 standard deviation to the right. Then if I add another 12.5, that gives me 104.4. That number is 2 standard deviations above the mean. So this is x bar plus 1s. This is x bar plus 2s. And then I'll add 12.5 and I get 116.9. And that's x bar plus 3s. Then I also need to find the data values that are below the mean. So I'm going to find the one that's 1 standard deviation less than the mean. So this time I'm going to subtract the standard deviation. 79.4 minus 12.5 gives me 66.9, and that's x bar minus 1s. And then I'm going to subtract another 12.5, and that gives me 54.4. That's the mean minus 2 standard deviations. And then if I subtract another 12.5, that's 41.9, and that would be x bar minus 3 standard deviations. Now, if the data distribution is bell-shaped, and I didn't make this very symmetric, I didn't draw a very good picture, guys. It should be more like, let me draw this right side a little better. The left side's pretty good. So what the empirical rule says is that if your data distribution is bell-shaped, then if you go one standard deviation to the left and one standard deviation to the right, do you see this space in here, from here to here? So these frequencies up here, it's saying that 68% of your data values will lie between those two numbers. Now, if you look at mine, almost all of mine lie between those numbers because you see all of them except the 60 lie between those two numbers. So it's at least 68%. And then if you go 2 standard deviations from the mean, so that's from here to here. So you have this 68% plus some more. Do you see? Plus you have this. So remember these data values that are in here are 68%. Now I'm adding on some more. I'm adding on these data values and these data values. You see I have a big percentage of that area under that curve. And in fact, from here to here will be 95%. That's a huge percent. That's all but 5% will be there. And then if I go 3 standard deviations from the mean, and if the data distribution is bell-shaped, then if I go that far, all the way from here to here, so from 41.9 to 116.9, then for that distance there, when I add on these two parts, then I basically have 99.7% of all the data values. This is true if the distribution is bell-shaped. So let's look at an example and see how that works. So I have an example, I think. No, I didn't do an example like this. I did an example of Chebyshev's theorem. So if I said from this, if I said, what percentage of the data values would be between 54.4 and 104.4? And you'd say, okay, well, that's the 2 standard deviations from the mean, so that's 95%. If I said, what percentage of the data values would be between 66.9 and 91.9? Say, okay, that's within 1 standard deviation of the mean, so that's the 68%. So this is how empirical rule works. Now, I did another specific example in my empirical rule lecture that's in the Unit 1 folder. I'm going to go on. I have a little bit of time, and I want to talk about Chebyshev's theorem. It also has to do, Chebyshev's theorem is what you can use if you don't have a bell-shaped distribution, or if the distribution, if the shape of it is unknown. And Chebyshev was just a person's name. It doesn't have any meaning by itself. Chebyshev's theorem can be applied to it can be applied to bell-shaped too, it just won't be as specific, it won't give you as much information. Can be applied to any shaped distribution, data distribution. So I'm going to share the empirical rule and what it says. So Chebyshev's theorem may be applied to data distributions of any shape, as I just said. And it is used to estimate. Notice it says estimate the minimum percentage, not exact percentage, but the minimum percentage of a data set that will lie within k standard deviations of the mean. So it's the minimum percentage within k standard deviations of the mean. Emphasize, it gives you a minimum percent. So the percent might be higher, but this is going to give us a minimum. So I'm going to show you this first and share that. So Chebyshev's theorem gives you the minimum percent within k standard deviations of the mean. And it's a formula to find this minimum percentage. And that formula is 1 minus 1 over k squared. K is the number of standard deviations from the mean. So if you're talking about within one standard deviation, except k has, I believe k has to be greater than 1. So because if you plug in 1, you're going to get 0 here. So at least 0% is within one standard deviation. That's true. But it will give you a minimum percentage that will be within a certain number of standard deviations of the mean for any shaped data set. Okay, so I'm going to do an example. I have a couple of minutes, so I want to do one example of this. And remember that I have other videos of lectures for these last two things in the Unit 1 folder. I also have a video for mean, median, mode in there. So, and I will put those, I'm going to have those closed captioned, and I'm going to put those in my stat lab as well, along with the recordings from today. So let's try to do one example in these last couple of minutes. I believe this is probably the example I do on the video. And this example says, from a sample with n equal 36, so it's a sample of size 36, the mean duration of a geyser's eruptions is 3.43 minutes and the standard deviation is 0.55 minutes. Using Chebyshev's theorem, determine at least how many of the eruptions lasted between 2.33 and 4.53 minutes. Okay, that sounds really complicated, but the first thing you're going to do is draw a picture. So I'm going to draw a picture. I don't know if it's bell-shaped or not. Notice it doesn't say anywhere that this is bell-shaped. So I'm going to, since I don't know, I'm going to use Chebyshev's theorem, but I'm still going to put the mean in the middle. So I'm going to draw a picture and then I'll share this with you. Well, actually, yeah. So I'm going to draw the picture on the board, but then I'll unshare this thing so I can show you what we're doing. So it says the mean is 3.43. So I'm going to draw sort of a number line and put 3.43 in the middle. And it says the standard deviation is 0.55. And this is a sample with n equal 36. Okay, so I'm going to unshare this, and they want to know at least how many of the eruptions are between 2.33 and 4.53. I'm just rewriting the problem. Okay, let me unshare this so that on the recording, they'll be able to see. So here I put the mean right here in the middle. I'm not drawing a bell curve because we don't know that this is bell-shaped. But I'm going to take this standard deviation. I'm still going to add it to the right and to the left. And by the way, I realize I've gone past time. So if you need to go, that's fine. You can look at this later. I've done the same example on that other video. But if you want to stay and see me do it this time, that's fine too. The first thing I'm going to do before I find how many, I'm going to find first the minimum percent. I'm going to do that first. And then I'll use that to find out how many. Okay, so I'm going to use Chebyshev's theorem. Tells me the minimum percent. I know the minimum percent is 1 minus 1 over k squared. So I've got to figure out what k is. Here's how you figure out what k is. Put the numbers on here. Take that standard deviation and add it 3 times to the right and subtract it 3 times to the left. So I'm going to find those same things that I found with empirical rule. So I have 3.43 plus 0.55 is 3.98. That's plus 1s. And then I'm going to add 0.55 again. Gives me 4.53. And notice that's the one I want for that upper limit. So that's x bar plus 2s. Then I'm going to go to the left and subtract. I'm going to find x bar minus 1s. So I'm going to take that 3.43 and subtract the standard deviation of 0.55. Gives me 2.88. And then I'm going to do x bar minus 2s. So I'm going to subtract the 0.55 again. I get 2.33. Notice that's this number. Okay? And that's x bar minus 2s. So when I'm going from 2.33 to 4.53, I'm talking about within 2 standard deviations. That's the number I needed. I needed to know how many standard deviations I was going to the right and left. And that number there, that's k. The number of standard deviations to the right and left is k. That's the k. That k is going to go right here in this formula to give me my minimum percentage. Some questions on Chebyshev only ask for the percent. This question is asking a little bit more. But a lot of questions just say, what's the minimum percent that are within 1.5 standard deviations or 2 standard deviations or 2.3 standard deviations? It doesn't have to be a whole number. But this one, I'm looking for first the percent that's within 2 standard deviations. So I'm going to have 1 minus 1 over 2 squared. You can do this in your calculator. If you do it in your calculator, put that in parentheses. But that's 1 minus 1/4. And it's okay to do this as a decimal. 1/4 is 0.25. This ends up being 0.75. So the minimum percentage is 75%. Now, they didn't ask me the minimum percent. They said how many of the volcanic eruptions or geyser eruptions are within 2 standard deviations. So this really meant within 2 standard deviations. That's another way they could have worded that, because that's what those numbers are. Those are the numbers we get when we add and subtract 2 standard deviations to the mean. So now what I'm going to do is I'm going to find 75%. So that's going to be 0.75 times the number of geyser eruptions there were. So I'm doing the minimum percent times n. And that's going to tell me the minimum number of geyser eruptions that will last between the 2.33 and 4.53 minutes. So I do 0.75 times 36, and that gives me 27. So it's going to be at least 27 of the geyser eruptions will last between 2.33 and 4.53 minutes. Now, it might be a lot more than 27. This is just a minimum. So Chebyshev's theorem always just gives you like the lower limit. It's going to be at least, that's a good word, at least that many. It could be a lot more, but it's going to be at least 27 out of the 36. It could be all of them. It could be all 36. But what Chebyshev's theorem tells us is that no matter what the distribution, if you're talking about how many or what percent will be within 2 standard deviations, it's going to be at least 75%. If your sample size is 36, that becomes at least 27 geyser eruptions. Okay, so that's all that's in this section. Be sure and watch the videos again if you need to see it all. And we only meet this one time this week, so you've got the whole weekend to get caught up and work on these different problems, watch the videos. So try to get all your homework caught up through 2.4 over the weekend, and be sure and try the proctorio practice. You might try that over the weekend too if you have time, because you're going to need to practice that before the test. So the 2 things, remember, you need to do before the test, which will become available on Saturday the 19th. The 2 things you need to do is send me a copy of a picture ID and do the proctorio practice. Make sure you do those 2 things prior to the test. You guys have a great weekend, and I'll talk to you on Monday.